Welcome to your guide to the citric acid cycle, where, under aerobic conditions, meaning oxygen is available, our bodies bridge glycolysis and our main production of ATP, the electron transport chain. To remember the CAC, ask, "Can I keep selling sand for money, officer?" Because why would the officer not allow you to sell sand anyway? Souvenir shops do it all the time. More importantly, the first letter of each word of your question represents each intermediate of the CAC. Before we get to the can of our question, we must first have oxaloacetate, one water molecule, and acetyl-CoA. Remember, acetyl-CoA comes from pyruvate under aerobic conditions, as well as amino acid and lipid breakdown. With all of these, and the help of citrate synthase in a condensation reaction, we produce citrate, a 6-carbon compound. Notice that citrate and can both start with C. Next, aconitase aids in the isomerization of citrate to isocitrate. Notice I and isocitrate both start with I. You get the point. This isomerization is a shift in the OH group from one carbon to another. NAD+ then gains an electron and is reduced to NADH. We get a loss of CO2, and isocitrate is oxidatively decarboxylated via isocitrate dehydrogenase. Our product? Alpha-ketoglutarate. Once again, NAD+ is reduced to NADH, CO2 is released, and a third factor, CoAsh, no, we didn't lose it, are all used in another oxidative decarboxylation reaction performed by alpha-ketoglutarate dehydrogenase. S-CoA replaces our carboxyl end closest to the ketone, and succinyl-CoA is produced, a 4-carbon compound. Unfortunately, this S-CoA doesn't stick around and is released as CoAsh. Cleavage of CoAsh requires the substrate-level phosphorylation of GDP to GTP. This in turn allows the phosphorylation of ADP to ATP via nucleoside diphosphate kinase. 1 ATP is produced. This all contributes to a hydrolysis reaction by succinyl-CoA synthetase to produce succinate. From succinate to fumarate, we employ the reduction of FAD to FADH2 via succinate dehydrogenase. Once again, water is introduced to allow fumarase to hydrate fumarate. Malate is our product. We're almost done. NAD+ is reduced for the third time, producing the third NADH via the oxidative enzyme malate dehydrogenase. We get our final product, oxaloacetate. But is this really the final product? No, because this is the citric acid cycle, and with the combination of acetyl-CoA, we start all over again. The coenzymes that aid in this cycle include TPP, derived from thiamine, FAD, derived from riboflavin, Mg2+, which is utilized in any kinase activity or enzyme that utilizes energy from NTPs, and lipoic acid. All in all, we get our final net reaction as shown here. Take note that each NADH produces 2.5 ATP and each FADH2 produces 1.5 ATP in the electron transport chain. Now study hard and expand your knowledge. This has been the citric acid cycle.